Hi, my name is Wentao Chen, and welcome to our talk on real-time simulation of violent boiling in concentrated sulfuric acid dilution. Concentrated sulfuric acid dilution is an essential yet hazardous experiment in chemistry education. Incorrect operations can lead to intensive boiling and even endanger the experiment operator. Therefore, we want to develop a virtual reality application for this experiment and enable students to conduct experiments in a safe environment. The most critical and challenging part of our system is to simulate the violent boiling process. Current methods focus on modeling the detailed interaction between water and bubbles, and simulate boiling phenomena with external heat sources and relatively calm fluid surfaces. While their method can provide realistic results by employing offline renderers, their method can be too expensive for interactive applications, and it is difficult to model violent boiling behavior with these methods due to lack of energy. The involvement of user interaction leads to another challenge. For instance, if the user is holding a container full of liquid and moves it with a relatively large acceleration, discrete collision detection will be missed, and as a result, a large number of fluid particles will penetrate through the container and spill on the ground, leading to an unpleasant user experience. In this work, we present a real-time approach to capture the chaotic dynamics in the violent boiling process. Our approach is highly efficient and can model boiling phenomena with different levels of intensity. Additionally, we introduce a new constraint type named Flask Constraint to remedy against particle penetration under extreme movement, which allows robust user interaction with simulated fluids. Finally, we built a virtual reality educational application that simulates the process of diluting concentrated sulfuric acid, allowing users to conduct experiments in a virtual environment. And this is a demonstration of our work in VR. First, we show the run operation, which leads to violent boiling. And now we show the correct operation. Before introducing our method, first we provide a brief introduction on fluid simulation. The fluid solver in our system follows position-based fluids, a particle-based fluid simulation method targeted for real-time applications. Position-based fluids follows the smoothed particle hydrodynamics formalism for spatial discretization. More specifically, a scalar quantity AI and particle I is approximately computed by a weighted sum of contributions from all neighboring particles. To enforce constant fluid density, position-based fluids solves a system of nonlinear constraints, with one constraint per particle. The first step of boiling simulation is to calculate the concentration and temperature using diffusion equation. For this, we use the diffusion equation proposed by Cummins and Rodman. Next, we need to calculate heat of solution, which is the quantity of heat evolved or observed in the dissolution of a substance. For concentrated sulfuric acid, a large quantity of heat is liberated when mixing with water. If a small amount of water is added to a large volume of a strong acid, the dissolution may produce a sufficiently large delta T that the water may boil violently and splash from the container, resulting in a safety hazard. The correct way to dilute concentrated sulfuric acid is by adding acid to water instead. Since water has a higher heat capacity than acid, the generated heat quickly dissipates into a large volume of water and preventing the system from overheating. Now we will briefly introduce the calculation. For detailed derivation, please refer to our paper. Given concentration and mass, we can calculate the amount of sulfuric acid and water contained by a particle. Then, we have this empirical equation to calculate Qk, the heat evolved upon mixing 1 mole of sulfuric acid with K moles of water. Using Qk, we can calculate the heat evolved upon mixing Na moles of sulfuric acid with Nw moles of water. Now, we can calculate the solution of heat as change of energy before and after dilution, and distribute the heat to each particle. Finally, we use a user-defined factor to control the influence of solution heat on temperature. Now that we have the temperature for each particle, we propose a method called anti-viscosity to simulate the violent boiling process with low performance overhead. Our method is adapted from the XXPH viscosity model. In this model, mu is a constant parameter with non-negative value to introduce energy dissipation. In our method, a viscosity coefficient μi is calculated for each particle depending on the particle temperature. The viscosity coefficient becomes negative for high-temperature particles, hence the name anti-viscosity. Normally, viscosity is used to introduce energy dissipation and enforce coherent motion between fluid particles. In our model, anti-viscosity works the opposite way and injects momentum into high-temperature particles and reproduces the chaotic behavior observed in violent boiling. Different from previous approaches, our approach does not model bubbles and works directly on liquid particles. This modification eliminates the complexity behind bubble dynamics, achieves better performance, and obtains better controllability over the fluid motion. In our system, user interaction and boiling simulation can make particles move at a really large velocity. Therefore, particle penetration will occur and result in unpleasant user experience. To deal with this problem, we introduce a new constraint type called Flask Constraint into our system. Flasks are common fluid containers in chemistry experiments, most of which are axis symmetric or close to axis symmetric. The key idea of our approach is to use a simplified analytic expression to represent these shapes. In this way, we can detect whether particles penetrate through the container at a low performance overhead. Here, we use a simplified 2D example to demonstrate our method. The simulation domain is divided by the flask into 3 regions: omega in, omega above, and omega out. Given initial position and predicted position for a particle, if the initial position is inside of the container and the predicted position is outside of the container, we know the particle has potential to penetrate through the flask, hence a Flask constraint is generated. When solving Flask constraint, the predicted position is corrected back into region omega in by projecting the position to the closest valid point in each axis. The extension to 3-dimensional space is straightforward. To support arbitrary axis symmetric shape, we sampled the radii of this shape on several horizontal slices during initialization, and stored this information into a lookup table. Moreover, during constraint calculation, particle positions are converted to the local coordinates relative to the flask, so that we don't need to deal with translation and rotation. In this way, we can easily determine whether a particle is inside or outside of its container. And given a potentially penetrated particle, we first project it vertically to a proper position. Afterward, we use the corrected y-coordinates to look up the flask's radius on current height, and project the particles towards the center on horizontal plane. Flask constraint is easy to integrate and has little performance overhead, but it's important to note that Flask constraint is not a replacement for conventional collision handling methods. Instead, Flask constraint is a safeguard mechanism used alongside traditional collision handling methods to avoid particle penetration during extreme movement. When there is no particle penetration, Flask constraint will not be generated, and thus have no influence on the physical accuracy of the fluid simulation. And this is the result of our proposed methods in various simulated scenes. In the first scene, distilled water is poured into concentrated sulfuric acid to produce violent boiling behavior. The second example demonstrates that our method can produce different simulation results when mixing different liquids. In this example, we show the different results of moving flasks with and without flask constraints. The final example demonstrates that our anti-viscosity model can also be applied to simulate other common boiling phenomena, and allows easy control over the boiling phenomenon's intensity. All demonstrations in our paper are simulated and rendered in real time. The results show that our method extends the capability and stability of position-based fluid solver with little performance overhead. There are some limitations with our current methods. Since the anti-viscosity method introduces extra energy into the system, instabilities or even explosion can occur if parameters are not set properly. Second, we omit some differences between sulfuric acid and water in our simulation, such as different viscosity, color, density, heat capacity, and boiling point. Considering these differences will provide an even more realistic simulation and higher performance overhead. Finally, our anti-viscosity model does not involve vaporization and condensation, which are also important phenomena in the dilution experiment. In our future work, we will investigate how to include phase changes in our model and improve visual fidelity. To summarize, we have proposed a comprehensive solution for simulating concentrated sulfuric acid dilution in real time. To capture the chaotic dynamics observed in violent boiling process, we propose the anti-viscosity model to inject momentum into particles with high temperatures. Additionally, we employ a constraint-based method to deal with the particle penetration issue arising from user interaction. This work improves the capability and stability of position-based fluid solver and provides appealing solutions for integrating fluid simulation into interactive applications. Thank you for your attention.